let's go to the introduction to the course itself, which is very much centered on the Vulkan API, which is a real-time graphics API for rendering stuff, for computing stuff. You can render with a rasterizer, you can render with ray tracing, you can render using compute shaders. As by, I think, December of January, you also have the possibility to encode video with Vulkan. So that has been released as a part of the standard. There's an extension for that, for encoding video. And this is interesting, of course, for the sister course, Cloud Gaming. And we have a working example for that, actually. So here are a couple of references. The first one is like the homepage of Vulkan, and the second one is probably the best entry point, or the third one, maybe the second and third one are your entry points if you really want to learn Vulkan. This is a very open list of resources, of learning resources with a lot of examples and so on. And this is the Vulkan specification remade in a more readable way. Okay, the initial Vulkan specification is a bit tedious to read. It's huge. It's like over 3,000 pages. There are different versions of it, depending on how much you really want to read. And this is a kind of a compressed version that really focuses on the things that are actually really important and doesn't bombard you with too many details. So docs.vulkan.org, I can really recommend it. Looks really good. Of course, there are also a lot of books you can read. These are the books I read. The first one is a really nice, gentle introduction if you really want to have a very, very slow-paced walk. The downside is that it really doesn't bring you to the end, so it's just like halfway through. But it's a more gentle approach. Of course, you can read these books and they're really helpful, but it doesn't save you from reading one of these sources like Learning Vulkan or docs.vulkan.org. That is really something that you should do in any way. So what are we talking about? We're talking about real-time rendering. So this is what we need in a computer game, obviously. Because when we are running a computer game, we have a very small amount of time to render a new frame. Usually we have about 16.7 milliseconds. This is 1/60th of a second. You should not get lower than 33 milliseconds because this is 1/30th of a second. This is when things really get bad, when you go below this frame rate. Or if you use more time than that. So if you're above 33 milliseconds, for instance, of course the CPU cannot do that. There's too much work to be done. So usually nowadays, like many decades now, we have specialized hardware. It's called a GPU, and the GPU will do the heavy lifting. You give it all the data. You say, okay, render that next frame, and then the GPU will render the next frame. It will draw all the objects that you have specified using the lighting, using the surface properties, and so on. There are basically three ways you can do this. One is to use a rasterizer. We will see this on the next slide. Another thing that has been developed in the last like 4 or 5 years to throw a ray tracer into the mix, which is a completely different way of looking things. And finally, which is something which is sometimes overlooked, you can also do ray tracing or even rasterizing by using a compute shader, which is kind of a general purpose way of computing. And you can program your compute shader like you want something to be created in parallel, like you can solve like differential equations or whatnot in parallel. If you want to do this really fast, you can do this with general purpose compute shaders, but you can also use them for rendering, of course. So this is the real-time aspect. So really, you really don't have that much time, like 16.7 milliseconds. That is your target or less. However, of course, traditionally, if you look at animated movies, Toy Story and everything that came afterwards, you could also render a movie in a computer, and that would be more offline rendering, of course. And there you would have seconds or even hours per frame. Usually you would do this on a CPU even. Nowadays, of course, you would have GPUs also and rely very much on them. And of course, because we're talking about movies and cinema and people would pay for that, you would really want to have the best possible quality, and that is mostly ray tracing or path tracing. So you get the best possible visual fidelity out of that. But this is not what we're talking about. We're talking about really the real-time aspect. Now, as I said, we have two basic options. One is rasterizing, one is ray tracing. And the rasterizer will take any object that you can triangulate. So here you have lots of triangles, and you have some kind of a photo paper, and then you will project it on a photo paper, and the result will be a projection of a triangle mapped onto the pixels of the screen. So these would be the picture elements of your monitor, which is represented internally as a chunk of memory, obviously, and then you would color all these pixels as being part of the triangle. So this is called the rasterizer. Now, ray tracing works completely different. There are two ways. Forward ray tracing would actually send virtual rays out from the camera into the world, and then you would have some kind of an acceleration structure where we try to determine whether this ray is actually hitting something. You shoot the ray out and you say, okay, is it hitting something? Is it hitting an object? And when it does, you can actually now calculate what does the object look like, what is the surface property of the object, what would be like a physically based model, how light interacts with the surface. And then you could do one of several things. You could actually decide to pretend that the ray is actually bouncing off, it's reflected somewhere else. You could try to send it directed towards the light and determine whether this is in shadow or not. Or you could actually try to shoot it through the object, because the object could be translucent in some way, and you can also try to shoot the ray through the object. And do this recursively until the ray actually hits itself some kind of a light source. And then you can do all the path, follow the path from the light source to the camera and determine the light that is actually seen from this object. So we see that there's a lot of work involved here for ray tracing. And that was the reason why, of course, the quality, visual fidelity is much better. So here we would have ray tracing, and here we would have like rasterizing. So the quality is much better, but there's much more work to be done for ray tracing. So this was considered to be impossible in real time until recently. So people came up with a kind of a hybrid between rasterizer and ray tracing, or full path tracing. And in the hybrid, you would actually first make a kind of an rasterized approach, looks like a deferred renderer. This is done by rasterizing, so you have a kind of an imprint of reality, and then you would use less rays just to determine shadows and lighting and reflections, ambient occlusion and translucency and things like that. So for that, ray tracing would be just an add-on to the rasterizer to make it more realistic, but still you would rely on the rasterizer. Nowadays, thanks to advancements in semiconductors, the newest generation of GPUs, in fact, can do everything with a full path tracer. We will have an example for that. However, there are still limitations. And either you do some kind of hybrid rendering, or if you are actually only using ray tracing, then you will not achieve the full goal of full resolution, high frame rate, and full path tracing. That's still not possible. So you have to fake in some way. So for instance, if this is your output of your ray tracer, you see you're not spending too many rays per pixel. Here, would be 1 ray per pixel, so 1 sample per pixel. So you have a lot of noise. You would actually then put it into a denoiser. And denoisers are very good these days. So this kind of, you're faking your way and still have a credible and very high fidelity output. So we need some kind of a denoiser, but also because ray tracing is still limited, we cannot ray trace in full resolution at full frame rate. So here we have an example. Here, this would be the newest graphics cards. NVIDIA has now the architecture Ada Lovelace, which is found in the RTX 4090, for instance. And if you look at Cyberpunk 2077, for instance, and which now, like for a year now, has offered something called RT Overdrive, and that's full path tracing. There's only path tracing. There's no rasterizer involved here, no longer. And when you measure what's actually the effort is, that you have 635 ray calculations per pixel. That's a lot. That's really a lot. And still, if you only use ray tracing here, you will be stuck at 16 frames per second, obviously at 4K. So obviously that's not really an option. 16 frames per second is not good enough. So what you can do, again, fake away and use machine learning for denoising, for frame generation and synthesis, and of course upscaling. And that is what DLSS 3 and 3.5, the newest version, actually do. So these are machine learning add-ons. They use compute shaders, obviously, or something like that to apply machine learning. And then when you have a very, very low frame rate, they can actually synthesize frames in between. So they look at how the frames evolve, they look at motion vectors, how the objects are moving in the frame, and then they are able to synthesize frames in between and really bring your frame rate from 16 to like 100 or more than 100 frames per second. Also, upscaling is something that you are likely to do because you would probably render at a somewhat lower resolution, and then you try to blow up the resolution by interpolating pixels. And DLSS 3.5, I think, has now a unified frame generator and upscaling. So they kind of put it together, and it's said to be very good. So we are really in a kind of interesting times where new technologies enable new stuff. However, this is not the norm. Not many people do have an RTX 4090. So still, most of the stuff is done in a kind of a hybrid way. On the mobile devices, of course, the hybrid is king. So you will have some kind of a rasterizer, and then maybe you can enhance it with a ray tracer on top of that. And in order to output all of this and make the GPU do stuff, you need to have a graphics API. So your programming stuff, you can choose any kind of modern programming language. Many people choose C++ for this purpose, but you can also use C or Rust or whatever. But of course, C and C++ are zero overhead languages. So they have this property that there's nothing in the background. There's no virtual layer behind between your program and the rough iron. You can directly translate your C++ program into assembler code or assembly code, right? So there's no layer in between, which means then if you're a skilled programmer, you can really get to the maximum performance that your CPU allows you to do. And that's why these graphics APIs are mostly, well, predominantly also meant for C or C++. And of course, traditionally we had the Windows world and the open source world. So the Windows world would be the DirectX path. Starting with DirectX 9, it was the first way of having these general purpose shaders, then 10, then 11. And of course, in parallel, we would have OpenGL for many, many decades now. And we will come to the shortcomings of this in a moment. But when people would work on their game engines, and these game engines would get better and better, they would find that all of these old approaches would actually be a kind of handbrake. So if you want to create a Ferrari and just always having a kind of a handbrake, because that's what you have to have with these traditional approaches. So around 2008, AMD and DICE, who have been creating their Frostbite engine, said they need something better than that. So they need a low overhead, low level API closer to the bare metal, allowing for multi-threading, allowing to make use of this new feature of CPUs. CPUs would have multiple cores, not only one, multiple cores, multiple threads, and also not rely on this handbrake problem. So they wanted to do something about it. So they came up with something called Mantle from the Earth, would be the mantle around the Earth. And from Mantle, the industrial organization Kronos then developed the Vulkan specification, the Vulkan API. Of course, we also have the other big players, Microsoft and Apple. They came up with their own versions. The ideas of DirectX 12 and Metal are actually pretty similar. So that all of them took the basic ideas. You want to get rid of this legacy stuff, of this blown up big fat driver stuff. You want to have something that is very slim, very flexible, give the programmers a lot of control, and also enable a lot of multi-threading and parallelism. So Vulkan, DirectX 12, and Metal are very similar in what they offer. Of course, they're not the same, but they're close enough that you actually can run Vulkan over Metal, and that's what Molten VK offers you. So Apple refuses to even look at Vulkan. So people from Kronos said, okay, let's try to have this kind of a translation layer. So they came up with Molten VK, and now they put Vulkan on top of Metal, and it actually works. Works pretty good, actually. So why is it actually a good idea to have this new approach, this completely new approach? Let's have a look at the traditional graphics driver. This was the situation for OpenGL or for DirectX 9, 10, 11. And the driver is provided by the producer of the GPU. So for instance, if you buy a graphics card from AMD, you get a driver from AMD. If you buy a graphics card from NVIDIA, you get the latest, hopefully the latest driver from NVIDIA. And the driver is a program. It is installed on your computer. And whenever you want something from the GPU, you will ask the driver. You cannot communicate directly with the GPU. So the driver is in between, will translate anything you want from the graphics card and sending data to the graphics card, getting data from the graphics card. And initially, these drivers or the approach was to make the life of programmers as easy as possible. If you program something with OpenGL or with DirectX, depending on if you use some kind of layer or in between, there's not much you have to do. So you can just say, okay, write the program in 20 lines of code and you render a triangle. Not a big deal with OpenGL. But that means that, in fact, in between, there's a lot of stuff happening. And the driver is now responsible for doing all the heavy lifting. The driver is a big, fat chunk of code, very complicated. There are hundreds and hundreds of person-years of development in a driver. It's super optimized. It has to deal with anything and everything you have to come up with. It has to be able to communicate with multiple devices, with the host, with a lot of GPUs cards, all of the GPU cards from the same provider. It has to do the synchronization, which is actually a big problem in itself. It has to prevent memory hazards. It has to do all the communication. It has to do all the memory allocation. And allocating memory for the data that you send up is something that, yeah, you can rely on some rule of thumb. But since the driver doesn't know what you really intend to do, it just can allocate memory on the graphics card as a rule of thumb. But it's not by no means a kind of an optimized way of memory allocation. Shader compilation, that was a big problem also. So that you would pass in the source code of your shader to the driver would compile it. That's very handy, that's very useful, probably. But if you go to the con side, we will see that the easy way is probably not always the best way. It's good if you want to write something within a day, I already said. But if you're developing your own game engine, that's probably not what you want. So what are the downsides? The downsides, of course, is that this driver is one monolithic heavyweight chunk of functionality. It is traditionally single-threaded, so you cannot submit stuff to the driver from multiple threads. Simply not possible. And that's bad for multi-threading, in fact. The driver doesn't really know what you intend to do in the next step and in the step after and in the step after, which means that when you submit work to a GPU, the driver really doesn't know when you will need to use that stuff. So for instance, you render into a texture and then you want to use the texture in a later step. There is a dependency here. We will come to these types of situations later on. So in fact, you have to wait until the rendering in the texture is actually done. You cannot use the texture before that, so you have to insert a memory barrier. And to prevent stuff from actually proceeding through the GPU that actually wants to make use of this texture, you have to wait until the texture is ready. Now, the driver doesn't know what you will do in the future, and it has no clue of your plans, which means that it has to do this kind of barriers and synchronization very conservatively. And there is a lot of time wasted here. However, of course, these graphic drivers have been optimized over the past, and they're super optimized, like super optimized. This is maybe not that big of a problem anymore. However, of course, when you update a driver, you can easily run into a situation when an old game doesn't work anymore, because the driver has been changed, has been optimized, has not been tested with a game that is 20 years old. Suddenly your old game doesn't work anymore. So concerning this single-threaded thing, usually the main thread of your game is overloaded because it tries to stuff work into the GPU, and all the other threads are doing nothing. They're not really doing anything useful. So you're really wasting a lot of time here just because there is no multi-threading support here. Let's have a look at a traditional game loop, what you are supposed to do on the CPU side. So this is your CPU side. You start your game, and then you enter this game loop. And in a game loop, what you do is first you have a kind of a timestamp. So this is the previous timestamp. And then once you're in the loop, you look at the current timestamp now, and you take the difference. And this is the time that has gone by since the last running through the loop. So you look at now, and then you take the difference, and then of course you store now in previous. And so whenever you run through the loop, delta time is now the time it takes you to go once through the loop and back. So this determines your frame time. And of course the frame rate. So one over the delta is the frame rate. So this is the first thing. Now you know delta t, this is the time that has gone by since the last loop, since the last I rendered a frame. So this is the time that you have to advance your game. So whenever you do physics calculations, advance my physics world by delta time. Whenever you have game logic, when you're moving stuff, when somebody's driving a car or having a motion with some kind of velocity, move on your objects by delta t. How far have they been traveling within delta t? Also, you have to react to user interactions like keystrokes, like mouse movement, like mouse button, scroll button, like your gamepad and things like that. So you have to tick that. So you have to poll that and react to that. Also, you might have some kind of AI component. Some of your NPCs might try to decide something. They decide to attack. They decide to run away. They decide to move somewhere else. You have some kind of pathfinding going on and so on. So lots of stuff that is going on in your game. All of this is running on the CPU. And once you're done, you are finished with moving your game along with delta t time. Then you have a new game state and you want to render the situation. So you want to make a snapshot of the game world, which means that you want to render the next frame. So what you can do is you somehow have to prepare the rendering. So whatever that is, in Vulkan terms or in DirectX 12 terms, this would actually mean to record the rendering commands. Okay. So that's work to be done. And previously, you would not record anything. You would simply submit render commands directly to the GPU. And because I said this has to be done single-threaded, there is no multi-threading. But now, with Vulkan, explicitly we can record all of this stuff in parallel. So all of this done work now can be done on multiple threads and more. And so we can actually bring this time down. We will see this in just a moment. And then we have maybe only one submit call. We've prepared all the work in parallel, and then we have one call, one submit. That's totally enough for Vulkan. We can record in several command buffers. We put all the command buffers in an array, and then we say submit this array of command buffers. This is one call. Previously, with DirectX 9, DirectX 10, whenever we would do a submit, we would actually have to do we would have to render call for every object. Think about it, you have to do all of this communication for all of the objects, like thousands of times. This was a nightmare for the performance. So they came up with this kind of recording and then submitting all the command buffers. So let's have a look at this situation. This is a traditional situation. We have the single-threaded driver. This is like the traditional way. We might even have multiple threads that are running and that we can make use of with our game. However, whenever we change something on the GPU, we upload data to the GPU, we change the state of some objects in the CPU, we submit command calls, and then the GPU is actually doing some work. All of this is done in a single thread. And all of these threads are actually doing nothing. Of course, we could do here some kind of thing in parallel, physics, simulation, networking stuff, reacting to user input, AI stuff. So that can be really heavyweight. But once we go into the rendering stuff, we can see there's a lot of potential lost here. But of course, modern CPUs have a bunch of different cores. We have many cores now, and each core, or more specifically, each thread of execution can be run independently of each other. It's called MIMD, multiple instruction, multiple data. Every thread of execution is something that is running independently of every other thread of execution and can do work. And this is what we want to do. We want to do work hopefully in parallel. And these cores share the whole main memory. It's like a unified memory architecture. They can also share caches, depending on the cache hierarchy where you are. Level 1 cache is probably owned by a specific core, but level 2 cache, for instance, is more likely being shared by at least 2 or 4 cores. Level 3 cache usually is shared by all of the cores, and then you have main memory, and you want to avoid every access to main memory as much as possible, because it takes like hundreds and hundreds of cycles just to access main memory. So caching is really important here. Now, on the complex instruction architectures like x86, usually this is what you sometimes have to do. You have to access main memory, and because of the instruction architecture, it's a bit clumsy and it's not very streamlined. Let's put it that way. So the possibilities to wait for main memory is quite high, and what they came up with is called simultaneous multithreading. And simultaneous multithreading means that every core actually is running 2 virtual threads. And whenever one thread is waiting for the main memory, because that takes a lot of cycles, then the core can switch to the second thread and do some useful work. And that actually is really a boost in performance, especially for these complex instruction set architectures. ARM and other RISC-like CPUs don't do that. Okay, so you won't find this on an ARM CPU probably, because that's not such a big problem on a reduced instruction set architecture, but on a complex instruction set, that's the legacy of the x86 instruction architecture, is that it's not streamlined or it's not optimized for that. So the bottom line is you probably have more threads than you have cores. You can query the number of core or a number of threads actually by calling this function, and this will give you the number of threads, not the cores, the threads. Okay, here we have a couple of newer CPUs that you can buy now for AMD. The newest one is the 7950X3D. It has 16 cores and 32 threads. And the others, the EPYC and Xeon line, they are the server types, and they have many, many more cores and many, many more threads. But so they're really meant for throughput only. Intel has its Core i9 version now, the newest 14th generation 14900HX. It has 8 cores with high performance and 16 efficiency cores. And you can see that the performance cores actually can run simultaneous multithreading. So 8 performance cores can run 16 threads, but 16 efficiency cores can only run 16 threads. So there's no simultaneous multithreading here. And Apple has something very similar. They also have up to 12 performance cores and up to 4 efficiency cores. And of course, this is a way to kind of have built in the possibility to have high performance workload, as well as being energy efficient and using up as little energy as possible. So why is parallelism such a good idea? So let's have a look at this frame here. So here, this would be a single-threaded game, and we have to do a lot of work, and then we record stuff, and then we submit it to the GPU, and then the GPU would work on it. While the GPU is working, we can actually start on the next frame, do the same thing. And once the GPU is finished, it will present the frame. So then we see the output of this computation. There might be some minor overlap here, as we can see, depending on the work you submit to the GPU, of course. And once you have a second frame, you know the frame time. This is the time between finishing 2 frames. And this is 1 over the frame rate. Now, when we can make use of many threads, then a lot of this work that is running only on the CPU can be done in parallel, obviously. Now we can make use of this in a much more convenient way. Some of these work packages will use more work, like the physics simulation maybe, or game logic or AI can use up a lot of work. I'll sit down here. But in the end, once you're done, you have to again record everything. This is done again in a single thread, submitted to the GPU. And when we do this in parallel, we see how the frame time is actually coming down. So hooray, this is our first result. By doing things in parallel, we have a much higher frame rate now. So how far can we go? Now this would be now so here we see that the CPU is actually the bottleneck. And what if we break down everything we do into very small chunks, submit it to all of the threads we have? We can do this, for instance, by using a job system. A job system is a way of starting a fixed number of threads, and then they wait for work. And you would submit smaller jobs to them, and whenever a thread has nothing to do, it will grab a job and and work on the job. So we have a kind of an optimized parallelizing of all of this workload here. And then, of course, and now Vulkan comes along, we can also do a lot of this preparation of rendering in parallel. And we see that suddenly the CPU is no longer a bottleneck, because in this very situation, we have brought down the frame time to its minimum possible, and now the GPU is the bottleneck. We can also try to optimize everything that's on the GPU. It's not so easy, perhaps, but it's possible to do all of many things in parallel on the GPU. Start threads, even starts rendering of overlapping frames. But you see that doing stuff, especially on the CPU in parallel, really is a good thing. Now, this was maybe the best you could do with OpenGL, and this is what you can do with Vulkan. Okay, so in a nutshell, this is what Vulkan promises you to do. So the next-gen APIs, they have a lightweight driver. It does much less than what a traditional monolithic driver would actually do. It is fit for multi-threading. A lot of stuff that is necessary, like resource managing and synchronization, must now explicitly done by the application. So I said that the driver doesn't know how you want to utilize stuff, how you want to use resources. Now, as an application programmer, you have to explicitly tell the driver, I want to have a barrier here, I want to have a dependency here, and then the system will do that, and hopefully in an optimal manner. Also, the driver no longer compiles any shader. What you do is, well, it kind of interprets it, but what you provide to the driver is a precompiled shader. So you don't provide a source code. You will provide an intermediate kind of a bytecode representation that has a very tight specification. So everything is super there are no loopholes, as you could find in previous monolithic drivers. We will come to this later on. And so there is no longer the problem that an older game wouldn't work, because these kinds of different interpretations between driver versions is a thing of the past. So here we can see all of these design goals that went into Mantle and, of course, then subsequently also into Vulkan. You would have scenarios where the CPU is like the bottleneck, or you have scenarios where the GPU is the bottleneck. And in each of these scenarios, you really want to have a kind of a mechanism to make use of parallelism, multi-threading, in order to bring down frame time and like get rid of this handbrake that you really don't need, and that's really not necessary. So one thing, for instance, low overhead validation and processing of API commands. In a traditional driver, the driver would always check errors. If there are errors, are you referring to objects that aren't really there, that haven't been initialized, that have been deleted, and so on? But if you are sure that your program doesn't have any error because you've debugged it, error checking is not necessary. So with Vulkan, you actually can switch on and off error checking. That's really, really very nice. So you save a lot of CPU cycles for something that's usually not really necessary. You can explicitly create command buffers, destroy command buffers, have a command pool where you can allocate command buffers. We'll see this in the next slide. You really want to make performance scale in a linear manner with all the multiple CPU cores and threads. So the more cores you have, the better the performance should be. Theoretically, that is one of the design goals. It's perhaps not 100%, but you can, if it's just CPU bound, then yes, you can really pretty much be there. Reduced runtime shader compilation. As I said, the driver doesn't compile anymore. It just gets a pre-compiled stuff from you, and then there's much less overhead in using that. And yes, of course, the draw calls, because you don't want to submit the draw call for every object you want to render. You want to collect all the draw calls into a command buffer and then submit only one command buffer. And then that can really speed up your time significantly. That was a major bottleneck previously. All the single submissions, whenever you said draw this object, draw this object, draw this object, there was a significant overhead for that. Now this overhead is simply gone. Yeah, and of course you want to make use of parallel CPU rendering support in some way. And so this is happening on the CPU, but what about the GPU? So whenever you do stuff on the GPU, again, you have a lot of stuff now that you can make use of. Reducing of command buffer submissions. Obviously, if you can submit only once, and with one submission you can submit like hundreds of command buffers if you want to. It's not recommended to use that many command buffers. Maybe so there is a rule of thumb, maybe 30 to 50, but you can have only one submission call and do that. Explicit control of resource compression and synchronization for the resources. You have compute queues where you can overlap compute and graphics workloads. So you can do rendering, then you can use some kind of a compute queue on top of the rendering and interleave that and make everything in parallel. Of course, you have to make sure that stuff is only used when it's ready. And that's what the synchronization primitives are for. So you have a lot of synchronization stuff in the GPU itself. Yeah, you have very flexible buffer and image access. You have built-in anti-aliasing optimizations and so on. So there's a lot of design goals, and all of this is now in Vulkan and is really improving performance. So let's have a couple of more things that we need. So I already said parallelization, multi-threading. That is really something that is key in Vulkan. Another paradigm that is really part of everything is create once, reuse many times, at least if you want to. And that refers to something, a peculiar property of the API. Whenever you make an API call, usually when we call a function, we give the function parameters. Now, it is not recommended to call a function with like 20 different parameters. And that's not what Vulkan does. For Vulkan, you will always have some, or mostly have some kind of a struct. You will fill the struct with all the parameters that you want, and then you will make the call and just pass on the struct. And that means that you have to fill the struct only once, and then you could actually save the struct and reuse it anytime you want. So without passing all these parameters onto the stack of the called function. Again, it probably doesn't save a lot, but if you call functions like thousands and millions of times, yes, then you will save actually a lot of CPU cycles. So create once, reuse many times. Resource pooling and caching. Also, very important performance optimization that is going on. Caching, obviously, as I said, on the CPU, caching is king. You really, if you want to program a game, you need to know how the caching works. Otherwise, you're really screwing yourself, okay? Know how caching works in a computer. Avoid accessing main memory as much as possible. Try to be as local as possible. Try to be in memory, in a predictable memory pattern. Use data-oriented design, not object-oriented design. This is something that people maybe don't learn on a computer on a university. However, in a computer game, you avoid object-oriented design as much as possible, right? Okay, so everything is a data object. Everything is lined in an array in main memory. Whenever you access a lot of objects, you do in sequence from top to bottom and go through all the relevant objects. This is cache optimal. Don't come up with your object hierarchy. This is like thinking of the past, okay? And probably that's why the Vulkan engine uses exactly that, object-oriented design. But in the future, use data-oriented design. Everything is a data object. You can have an object hierarchy for stuff that actually is important, like managers, managing objects and communication objects and so on. But data in your game, non-player character data, position data, or orientation data, that is data, and you put it into an array. Caching with respect to Vulkan, there is one very important caching mechanism. It's for pipelines. We will see how that works when you want to like create a state, a render state. You do this by creating a pipeline, and a pipeline is like a super object. Like it's super big. It contains a lot of stuff. All the state that you want to use at a certain point, you put it into a pipeline. So creating a pipeline is a heavyweight operation. It takes a lot of time. You don't want to do this over and over again. That's why you do it once when you start your game. And a lot of games actually create hundreds of pipelines, which is a kind of a state at the start. So when you start your game, and then you wait, and then you wait, and then you wait, and there's a sandbox or like a progress bar, like 10 seconds go by, and the computer is still creating all these pipeline objects. But we said that we create once and reuse many times, and Vulkan actually provides you with this possibility. So once you have created all these hundreds of pipeline objects, what you can do is you can create the pipeline cache, and the pipeline cache will provide you with a big blob of bytes, and you simply push all these bytes into a file on the disk. That's it. Next time you start the game, you simply create a pipeline cache and feed all the bytes from the file back into the pipeline cache, and suddenly you have all the pipelines, all the hundreds of pipelines recreated within a second. Okay, so pay once, but reuse many times. Obviously, yes. A pipeline represents a render state. We will see this later on, but you have to tell the GPU how you want to render stuff, right? How the input data looks like, how the blending looks like, what kind of shaders you want to use. Okay, and all of this stuff has to fit together. You can't use this shader if the data that is flowing into the vertex buffer and index buffer don't fit together. So you create the pipeline state. So I want to use this shader with this vertex buffer, with this index buffer, with this blend state, and so on and so on. And then you have one pipeline object where everything fits together. Okay. Yeah, we have one of the bachelor thesis that was completed last year was a kind of a GUI for Vulkan, and you can play around with it, and you can create your pipelines yourself by just clicking on the GUI. I'll put the link into the Moodle later on. So you can really play around and see how it actually looks like. The tool is not 100% finished, and we will continue working on it, but that was actually a bachelor thesis that we did. Pooling, what is pooling? Well, we will see two pools in Vulkan. And pooling is actually always a good idea because pooling means that you pre-allocate memory and then you can allocate stuff in the memory. And we will see that in this pool, everything has the same size. Now, if everything has the same size, allocation and delocation is really, really quick and easy. So for instance, you just have a bit field, and if this tile here, this slot, or this slot is still available, then the bit is 0. If you allocate it, then the bit is switched to 1. And if you want to deallocate stuff, well, set the bit to 0 again. That's it. That's all you need if you make it intelligently to deallocate stuff. Of course, that works only if all of these things have the same size. If you have different sizes, then the whole bit idea doesn't work anymore. Also, we see that switching from 1 to 0 wouldn't really trigger some kind of a destructor. So if you're using a complex C++ classes that rely on a destructor that doesn't work, you would have to call the in-place destructor, which you can do. But if everything is just data, you really don't need that. Okay, so if everything is data, like a vector, like a matrix, you don't need constructors and destructors. So having these pools, which are really just data, is a good idea. And Vulkan actually does that for command buffers and for descriptor sets. And also reducing overhead when making a draw call. We can pre-record command buffers, put them all into an array, like an array with 50 command buffers, and then just map one draw call, command draw, and then all of these buffers are sent to the GPU. That's really a big performance win here. As a bottom line, Vulkan gives you a lot control, much more control. However, you have to make use of it. You can totally screw everything. You can totally mess up everything. You can totally mess up the performance. If you're lazy, if you don't really care, then you will have only like 10% of the possible performance. If you put in a lot of care and work, then you can really squeeze out all the possible performance that's possible, but you really have to put in a lot of work. So here we have a couple of next-gen APIs. We have DirectX 12, we have Apple. Of course, this is more or less running only on Apple, on the Apple ecosystem. This is running only in the window ecosystem. Vulkan is really running on all of these things. So this is really cross-platform. And you can also run it, as I said, with some kind of translation layer on Apple. So it's also really meant for mobile platforms. So who is actually responsible for Vulkan? Now there is an industry association, it's called Kronos. There are two possible ways to interpret this name. There are two Kronos figures in the Greek mythology. One is the Greek god of time, one is the father of Zeus. Take your pick. I would go for the god of time. It's an industry consortium. It's open source, royalty free. You get all the standards. It's really amazing. It's financed by the industry to come up with specifications and standards that are cross-platform. And then there is a company. It's called LunaG, and LunaG is paid by Kronos to implement stuff. So they provide the software development kit and a lot of tools. Super tools, really very nice tools, very useful tools. All of them, for instance, I think they are running all the documentation stuff and things like that. So they are like the executive arm of Kronos and create stuff that you actually can download and compile. And then there are many technical subgroups, of course. One of them is the portability technical subgroup that actually creates the Molten VK translation layer for Mac. Now, there is a big history, of course, as we have seen. 2008 was like the begin of all of this. But in the 1990s, we had the begin of OpenGL. So we can see that there's a big legacy here. And it's a lot of weight, of that weight that has been pulled. Of course, OpenGL has been as much improved as DirectX. But we have seen it has been relying on ideas that were good at the time in the 1990s. but nowadays they are really not that good anymore. So we need more. We need a better approach to that. Here we have also something that's called Spear. We will see this in a couple of slides. This is for representing graphics and parallel compute stuff, and Vulkan will make use of this. This is this intermediate representation of our shaders. So when we create shaders, we create source code, we compile the shaders into Spear V, and this is then what we feed into the graphics card. This is what we give to the driver, and the driver will receive Spear V bytecode and then will again make some kind of a translation. But this time there is nothing to interpret. This is like a tight specification. There is no room for different interpretations here. Yeah, so here we have a comparison between OpenGL. We have different versions for mobile and for PC. Vulkan doesn't need that. Vulkan is one specification to bind them all. So here we have a big monolithic driver that is doing all of this, some error management. Driver processes the shading language, complex driver, a lot of overhead, cross-vendor unpredictability, and things like that. And now the Vulkan driver is, and on top of that is your application. And the Vulkan driver is more this approach here. So this is really like an abstraction of the graphics driver itself. And a lot of stuff is done by your application. Now we already see the difference. This is you programming OpenGL. This is you programming for Vulkan. You can see the difference. Okay, and this is why you need about 1,200 lines of code to draw a triangle. Now that sounds ludicrous, and it kind of is, but once you have created all the stuff necessary, you're good to go. You have everything, you've done everything, and then you have a lot of fine-grained control about that. So we have simple driver, we have layered architecture, so you can switch on and switch off validation and debug layers and so on. We have only this Spear V intermediate language. There's no, you don't feed in your shader text. And it's a unified API. You can use it for mobile, desktop, console, embedded platforms. It's always the same core language. Threading use cases are especially encouraged. That's what we want. We want to use as much as parallelism as possible on the CPU and the GPU. So we can update buffers on the GPU in parallel. That is something that is a first-class citizen. If we send data to the GPU, we can do this in parallel. Vertex, index data, animation data, morphing data, uniform buffer updates, all of this can be done from different threads. You can create pipeline state objects in parallel. As I said, this is something you have to do it before you use the GPU. You have to kind of create this state object, which is big. It makes sense to do this in parallel. We can also dump it onto a cache. So even though in theory this would be a huge chunk of work, in practice you can really bring it down to under a second if you have done it once. Threaded rendering, draw calls, that is very, very important because you do that every single loop. Every single loop, you make a draw call, draw. So this is where you really want to do as much as parallelism as possible. And most of this is actually in generation and recording of command buffers in multiple threads. So we are recording what the GPU should do, and then we submit it. But however, submitting is not thread safe. We cannot just bombard the GPU with submissions from many threads. However, as I said, it's totally okay if you do this only once. If you collect all the command buffers and do this only once, that's up to you if you want to do this. Or you could actually start submitting command buffers from a specific thread as soon as the work that you have recorded is ready. Okay, think about it. So for instance, if you get a new frame from the swap chain and you say, okay, I want to record my new frame, what you can immediately do is to clear the frame. or if you know where the camera is, you can immediately render all the static world geometry. You don't have to wait for all the game objects, actually. You can do this immediately. Once you have the frame, you can immediately render all the static world geometry. You just need to know the position and orientation of the camera. So again, you can do a lot of stuff in parallel and start rendering even before you are finished. And that is one of the optimizations that's really very tricky. And this is really up to you if you really want to go that route. Yeah, we have seen a slide before, learning Vulkan. There's lots of very good sources. This is now my go-to source. I will read through this again. You have the Vulkan tutorial, which has been moved also to the Kronos homepage. We have these learning resources here. Vulkan in 30 minutes. I found the title very amusing, let's put it that way. It'll just give you a kind of nice ideas, but don't expect this to be enough to understand Vulkan. This is maybe more interesting, understanding Vulkan objects, what they are for. That is actually the task of this course here. What Vulkan objects are there? What can I use? What can I use them for? How can I create them? How can I use them? How can I destroy them? That's it. That is what you have to learn in order to use Vulkan. And of course, there are cheat sheets. The specification, that's a lot to digest here. Lots of books. Good examples from Sasha Willems, both in C and C++, and so on and so on. So this is the bottom line. Understand what the API objects are for, how you use them. And it turns out that once you're through them and you have a good grasp, and then it's not that difficult. It's just you have a lot of options and choices to make. And even if you don't want to build the best possible product, you can really come up with a pretty good one. A couple of important things to know. Vulkan comes with the idea of layers and extensions. These are really two key ideas of Vulkan. Layers are attached to an instance. They were always also possible in the previously at a specification 1.0 for devices, but it turned out that really doesn't make much sense. There's no need for that. So that is actually deprecated, and instances now can have layers. So what does that actually mean? An instance is like an entry port into Vulkan. So whenever you program something for Vulkan, you start your program. The first thing you do is create a Vulkan instance. It's like a context that you would have to create for on the Windows graphics API. You create an instance of Vulkan, and then this is like your entry point, and for dealing with Vulkan, like as I said, a context for that. You do this only once. It's very easy. Just create instance. That's it. There's not much to it. However, when you do, you can actually query what kind of layers are available, and then you can actually switch on and off layers in your program, or you can use a config tool to do that. And so what I've talked about now so far is what is a layer? What is a layer? And a layer is something very handy, because I talked about, for instance, error checking. So whenever you make a call into a Vulkan function, if the call belongs to a specific class, like there are 5 classes of calls that relate to layers, then the call will actually be diverted first to the layer that you have enabled, like error checking layer. Okay, you switch on error checking. Suddenly you have between your call and Vulkan, you have a layer error checking. So whenever you want to make a call, it goes through error checking. So this is very handy if you're developing your program. And the task is really to get rid of all of the Vulkan warnings and errors. So this is the biggest thing you have to do. Once you have got rid of them, switch off the error checking. Don't enable it, and there is no more error checking. So that is one layer. And there are many more layers. So for instance, you can use a layer for writing the the frame rate into the title bar of your window. Why not? There is a layer to modify calls. There is so these are really layers that you can add, and then your calls will have to go through all the layers, and finally they actually do what they're supposed to do. And you can switch them on and you can switch them off. We will see this later on. It's fairly easy. You just query for a specific layer. Is the layer there? And if it is there, you can say, yes, I want this layer, or no, don't use the layer. You can use a config tool that has nothing to do with your program in order to enable layers or switch off layers. That's probably the preferred way to do that. And then you can see the output of. So when you start your program and you have a warning, then in the console, you will get all the warnings from the specific layer. So you have to query whether the device supports the layer or the driver, more or less, must be switched on explicitly. And yeah, you can have error checking debug output. So there is a debugging layer that really will output every call you do. It will output the call and all the parameters for that. So you can really see in the debug output all of the calls you have been doing and check whether this is what you would be expecting. And statistics and so on. So many different layers. Okay, so layers is something you can switch on, you can switch off. But what about extensions? Now, extensions exist for instances and devices, which means that different devices can have different extensions. And the idea is that Vulkan comes with a core functionality that every platform must support. So, like for instance, with specification 1.3, you have timed semaphores. Every single Vulkan implementation must support timed semaphores. It's part of the core standard. Doesn't matter if it's on a mobile device, if it's on Windows, if it's on Linux, doesn't matter. Every one of these drivers have to support that. However, there might be functionalities that a high quality graphics card on your PC supports, but a mobile device doesn't. Or a mobile device supports tiling and a PC doesn't support tiling, because on a PC it doesn't really make much sense to use tiling. And so people came up with this idea of extensions. So you have to, if you really want to make use of an extension, you have to ask, is a specific extension supported by this platform? If yes, you have to specifically enable it, and then you can use it. And then you can make a call specific for this extension and use that. But these are actually something that's not guaranteed to be there. Quite often it will be there in some way, but sometimes you don't rely on that. So extension is everything that's not part of the core standard. Vulkan and mathematics. Mathematics don't really matter to Vulkan. It's agnostic to that. You can use any kind of mathematics package you want. You can, usually I use GLM because that is a widely available, very handy, very, very well designed mathematics package with up to 4 dimensions. That's all you need. You could also use DirectX Math. You can use any kind of other language or library for that matter. All you upload are floating point numbers to the graphics card. Doesn't matter where that actually comes from. So that's really up to you. This is how the pipelines look in a modern graphics card. This is what we will have a look at. This is the pipeline. We will pour work into the pipeline, like draw triangle 1, draw triangle 2, draw triangle 3. What comes next? Draw triangle 4. 5, 6, 7, okay? All of this work, like in an assembly line, will flow through that and will finally be pushed onto the color output, okay? So the work flows in, draw this, draw that, wait for that, make use of a texture. So here we have resources like texture buffers, like vertex buffers, like index buffers, images that we sample from uniform buffers where we have some kind of position and orientation data. And we can make use of these buffers at every one of these stages. Well, the stages here that are yellow are stages where we can actually put in our own data, our own program, our own shader. We can come up with a vertex shader, a tessellation control shader, evaluation shader, geometry shader, and fragment shader. This is where we can put in our shaders. So when we say we program a shader, we also have to tell Vulkan where the shader should land, one of these slots. And then our program is running using one of these data things. And this is part of a pipeline object. So whenever we say, please, Vulkan, use this pipeline object, we really mean use this vertex buffer, this index buffer, use a shader for here, use a shader for here, and use a shader, this shader for here. This is a pipeline object. This is what a pipeline object will configure the whole pipeline. Everything that's happening here. And that's why it has so many different parts, and it's a heavyweight object. Now here we have a frame buffer, what's called a frame buffer. It has a couple of images attached to it. Let's call them input attachment and out and color attachments and depth stencil attachments. So these are images. And whenever we draw something, it will land on one of these images. And this is then our output that is shown. So that's more or less it. Of course, we will go there in more detail. Yeah, programming shaders. These are the shader programs that we program. There are lots of different languages. So GLSL, of course, is one of the oldest. HLSL is from Microsoft. They are quite similar. However, there has been a big update on HLSL. So we are now with the 2021 version. Which is quite a significant step, I must say. Now enables templates and so on. But in the last time, of course, we have seen a plethora of more shader languages. So WebGPU shading language now is really coming up and coming. NVIDIA is now proposing a new shading language called Slang. And there is a reason for that, because GLSL, because it's so old, it's not really up to the task anymore. It really is like a Frankenstein's monster. It can do everything, but it's not really a programming language that you would like to use. So there is a huge need to have a kind of a next generation shader language. And so these are more new approaches to find a new way to like program all of these shader stages. And we will see which one of them actually prevails. But as we see, all of them we can actually put into SPIR-V. And then SPIR-V is the standard portable intermediate representation language for Vulkan, SPIR-V. And it's a cross API standard, fully defined by Kronos, and native support for shader and kernel features. You can use it for OpenCL, for instance, for compute stuff, OpenGL, Vulkan, SYCL, whatever. It's actually a high-level intermediate language. It's really like a language. It feels like a language, but you don't have it in a textual form. You have it in a binary form. It's like a bytecode. And you can use a couple of tools when you install the SDK. You get a couple of tools like GSLang Evaluator, for instance, or Shader RC. You can use these tools to turn a GLSL text file into a vertex shader or in SPIR-V. So just call this, give it a text file, and it'll give you a SPIR-V file, and that's it. So it's as easy as that. And the output, the SPIR-V, for the programmer, the SPIR-V is just a blob of binary data. It's just bytes. So what you do is you load the bytes from file, put it in main memory, and then when you create the pipeline object, you simply say, I want to use this shader for a vertex in this pipeline as a vertex shader, and it's just a blob of bytes. Do whatever you want with it, and magically it works because it's SPIR-V. So SPIR-V is not just simple like something, it's really an ecosystem. So we see that we have GLSL, we have HLSL. We can use GSLang Evaluator to turn all of these into SPIR-V. DirectX, DX cross compiler. Also, we can use LLVM to turn all of these things into SPIR-V. There are cross compilers for metal shading language, HLSL and GLSL, also turning these into SPIR-V, and so on. We have things for disassembling, we have a validator, and so on. So this is really a big ecosystem providing tools for a lot of pretty much everything you can think of. So almost done for today. One big thing that we will have a look at is synchronization. As I mentioned before, you have many objects. A lot of work is done in parallel. Some work might depend on the finishing of other work. That's called a dependency. And you have to make sure that dependencies are really taken care of. That means that we have to synchronize stuff. Also, not only between the GPU and the CPU. That is pretty simple, but mostly inside the GPU. So let's say you submit work, first turn something into a texture, and then immediately afterwards use this texture to do something. So there's a dependency. So the second command needs to use the output of the first command. But if you pour work into a pipeline, all of this work actually can be done completely in parallel. There's absolutely no guarantee that the second command will wait until the first command is finished. In fact, when you pour in a lot of work, like parallel work, at some point it will overlap. It will be done in parallel. But you can't start with the second command until the first command is finished. So you put in a barrier, for instance. Wait until this is finished. And then that's taken care of. But this is something you have to do. So here we have a couple. These are these 5 classes where you can actually have some kind of a layer intercepted. That's called a dispatchable object. Anything that uses a VK instance, a physical device, command buffer device, or queue in its call is a so-called dispatchable call, and these are dispatchable objects, and they get their own handles. So we will see what a handle actually looks like. There is, if you look at the docs here in the fundamentals chapter, that is very well specified. When could you use what, and when you create it, when can I use it as a parameter, and so on. So that's really a big point here in the fundamentals. Yeah, and if you don't do that, then your program will not work. It will have completely undefined output. Now, last slide for today, Vulkan API overview. These are objects. We will not have a look at all of them, but most of them. But 30 object types in the core specification of Vulkan. Some are new or coming new, like a timed semaphore, for instance, that was new in specification 1.3. Otherwise, it's pretty much stable, and Vulkan will grow in its functionality only with these extensions. So we will go through all of these objects. Now, this looks intimidating, obviously, but we will see that there are some groups, like for instance, here we have a descriptor set layout, we have a descriptor pool, and we have a descriptor set. So everything starts with a descriptor. So you can imagine that this is more or less the same idea here. It's just a way to make it more flexible and more performant. Otherwise, it kind of belongs together. Or here we have pipeline objects, here we have a pipeline layout, and here we have these shader modules and a pipeline cache. So again, these 4 things are actually very much interlocked with each other. So this is actually one idea. So immediately you can see, okay, even though it looks like a lot of objects, if you break it down, there's much less complexity than actually looks like. Otherwise, we have here memories, for instance, memory heaps, memory types. Again, this is more or less the same idea. Device memory here. So in a nutshell, we will go through all of these objects, understand how we can create them, use them, destroy them. And that is the end of my talk for today. Thank you.